Hello guys, welcome to our comprehensive series on pattern recognition in computer science. In this course, we will explore the fundamental concepts and advanced techniques that drive this fascinating field. From the Bayesian decision theory to the hidden Markov models, we will cover it all. And you will learn about the practical applications, real-world examples and the latest tools and libraries. So whether you are a student, a professional or just curious, this series is designed to enhance your understanding of pattern recognition. So let's dive in and start uncovering the patterns in data together. So, introduction to pattern recognition. Pattern recognition is an automated process of recognizing the patterns and the regularities in data through the use of algorithms and machine learning techniques. It is a fundamental in enabling the machines to perceive and interpret the data in ways similar to the human cognition. The importance of pattern recognition lies in its vast range of applications that significantly enhance the various technological capabilities and efficiencies. For instance, in image recognition, algorithms can identify the objects, faces, and scenes within the image, revolutionizing fields such as security, healthcare, and social media. In speech recognition, the system can understand and process the human language, leading to advancements in virtual assistants and transcription services. So some examples of pattern recognition tasks, like the common task in pattern recognition, include the optical character recognition (OCR), which involves converting the different types of documents such as scanned paper documents, PDFs, and or image captured by the digital camera into editable and searchable data. Another example is biometrics, where systems recognize the individuals based on physical or behavioral traits like fingerprints, retina patterns, or voice. Additionally, spam email detection, fraud detection in banking, and recommendation systems in e-commerce are all reliant on robust pattern recognition mechanisms. So, application in various fields like pattern recognition is pervasive across numerous fields. In healthcare, it aids in the early detection and diagnosis of disease through the medical imaging and genomic data analysis. In autonomous vehicles, it enables the recognition of roads, signs, obstacles, and other vehicles to ensure the safe navigation. In finance, industry use pattern recognition to detect the fraudulent transaction and access the credit risk. Furthermore, social media platforms leverage it to filter the content, suggested contents, and enhance user experience through the personalized content recommendation. Okay, so now the components of pattern recognition system. A typical pattern recognition system is comprised of three main components: sensing, feature extraction, and classification. Sensing involves the collection of raw data through various sensors or input devices. For example, in image recognition, cameras capture the image. In speech recognition, microphones record the sound waves. Okay. So feature extraction. Once the data is collected, the next step is feature extraction. This process involves identifying and isolating the most significant information from the raw data to form a feature vector. Features are the specific measurable properties of data, such as edges and textures in an image or phonetic elements in speech. So effective feature extraction is crucial as it directly impacts the accuracy and efficiency of the subsequent classification process. So now, classification. The final component is classification, where the extracted features are analyzed and assigned to predefined categories or classes. This step involves the use of various algorithms such as decision tree, neural network, and support vector machine to make prediction or a decision based on the pattern recognized in data. So the overview of pattern recognition process, like pattern recognition process generally follows a sequence of steps starting with data acquisition through sensing, followed by pre-processing to enhance the quality of data. Okay, feature extraction then transforms the data into a more manageable form, emphasizing the relevant patterns. So finally, the classification steps interprets these patterns to make informed decision or predictions. This structured approach enables the systems to effectively and accurately recognize the patterns, driving the advancements across the numerous industries and applications. Okay, so now the Bayesian decision theory part 2. So introduction to Bayesian decision theory. This is the fundamental statistical approach for decision making under the uncertainty, which incorporates the Bayes theorem, So you are familiar with Bayes theorem, right? Already you studied in statistics and mathematics. So Bayes theorems to update the probability estimates as more evidence or information become available. The basic concept revolve around understanding and utilizing the probabilities to make the optimal decisions. So key terminologies include the prior probability, okay, the likelihood, and the posterior probability. So the Bayes theorem, which mathematically express the relationship between these probabilities, is central to Bayesian decision theory. It is given by the formula you can see in the screen here, the PH/E. Okay, so H by U you can read equal PE by H into PH by total PE, probability of E. Okay, so the posterior probability of hypothesis H given the evidence E. Okay, so PE/H or E by H is the likelihood, and PH is the prior probability, and PE is the marginal likelihood of the evidence. Okay, so Bayesian classifiers. Bayesian classifiers use Bayes theorems for classification task, predicting the class membership of a given data point by calculating and comparing posterior probabilities for each possible class. So simple Gaussian classifier. Assume that the data for each class follow a Gaussian distribution. Gaussian means normal distribution. The parameters for this distribution, means mean and variance, are estimated from the training data. So the classifier calculates the probability of a data point belonging to each class and assign it to the class with the highest probability. Okay, so multivariate Gaussian filter. It extends the simple Gaussian filter to handle the multiple features by assuming that the features vector for each class follow a multivariate normal distribution. This involves estimating a mean vector and covariance matrix for each class. Decision boundaries and risk minimization. The decision boundaries in Bayesian classifier are determined by comparing the posterior probabilities of different classes. Risk minimization involves making decisions that minimize the expected loss, which is calculated based on the posterior probabilities and the cost of different types of classification errors like false positive, false negative, means the confusion matrix. Okay, so examples and applications, like a common practical example is spam email detection, where Bayesian classification evaluates the probability of an email being spammed based on the features such as wrong frequency. Okay, so another example is medical diagnosis, where the probability of a disease is assessed given the symptoms and test results, helping doctors to make informed decisions. Okay, so real world application like email filtering, medical diagnosis, finance, speech recognition. Okay, so Bayesian decision theory provides a robust framework for making the informed decision by systematically incorporating the new evidence, making it individual in diverse field where uncertainty and the variability are inherent. Okay, so now this is time to discuss about the parameter estimation methods, the part 3 of our video. Okay, so introduction to parameter estimation. So parameter estimation is a crucial process in pattern recognition. It involves the determination of the parameters of the underlying probability distribution that model the data. Accurate parameter estimation is essential because these parameters directly influence the performance and accuracy of pattern recognition systems. For instance, in a Gaussian classifier, the parameters of Gaussian distribution, means mean and variance, must be accurately estimated to ensure the proper classification. So methods of parameter estimations. So there are several methods for parameter estimation, each with its own principle and application. Like first is maximum likelihood estimation, MLE. MLE is a widely used method that estimates the parameters by maximizing the likelihood function, which measures how likely it is that the observed data was generated by the model with a given set of parameters. Mathematically, if theta represents the parameters and x is a set of x1, x2 up to xn is the observed data, the likelihood functions is L of 0/x. The MLE is a value of the theta that maximizes the L 0/x, capital X. Okay, so for example, you can see in this screen. Okay, So you have a Gaussian distribution with parameters mu and variance. Means and variance is given. The MLE for mean is a simple mean, and for the variance, the sample variance, you can see in this screen the formulas. So Bayesian estimation. Bayesian estimation incorporates the prior knowledge or beliefs about the parameters along with the observed data. It combines the prior distribution of the parameters with the likelihood of the observed data to form the posterior distribution using Bayes theorem. The estimate is typically the mean or mode of these posterior distributions. Okay, so if theta is a parameter to be estimated and p theta is a prior distribution, the posterior distribution p theta slash x is given by, you can see this formula in the screen, where the px is the marginal likelihood. So comparing, we can compare this like MLE is the straightforward and often easier to compute, but it relies on the solely on the observed data without considering the prior knowledge. So Bayesian estimation incorporates the prior information, making it more flexible and robust, especially with the limited or noisy data. However, it can be computationally intensive due to the need to calculate the posterior distribution. So some practical examples you can see in this screen, and application like medical diagnosis, finance, engineering in signal processing, the parameters of noise distribution are estimated to improve the signal extraction and reduce the interference. So in summary, the parameter distribution is parameter estimation is a fundamental step in the pattern recognition, and methods like MLE and Bayesian estimation provides a powerful tool to derive the accurate models from data, enhancing the effectiveness of various applications across different fields. So now this is time to discuss about the hidden Markov models for sequential pattern classifications. Okay, so the basic concepts. Hidden Markov models are the statistical models that are used to represent the systems that follow a Markov process with hidden states. In a hidden Markov model, the system is assumed to be a Markov process with unobservable or hidden states. However, each state emits observable output which provide the indirect information about the hidden states. Structure and components of hidden Markov model, like state, observation, transition probabilities, emission probabilities, and initial probabilities. You can see in this screen. Okay, so training and using the Markov models. So forward backward algorithm. So the forward backward algorithm is used to compute the probability of a sequence of observation given the model parameters to estimate the most likely state sequence. It involves two steps like forward procedure and backward procedure. Okay, so you can see the formulas. Okay, so Viterbi algorithm. The Viterbi algorithm finds the most probable sequence of hidden states, means the Viterbi paths that results in a sequence of observed events. It is a dynamic programming approach that maximizes the probability of the state sequence. Okay, so applications. So speech recognition. So Markov models are extensively used in speech recognition to model the sequence of phonemes in spoken language. Each phoneme is represented by an HMM and the sequence of words is decoded using the algorithm like Viterbi to find the most likely sequence of phonemes corresponding to the observed acoustic signals. So bioinformatics. In bioinformatics, the HMM are used to model the biological sequence such as DNA, RNA, and protein sequence. They help in identifying the genes, predicting the protein structures, and understanding the evolutionary relationship. For example, the HMMs can be used to find the motifs or conserved regions in DNA sequence, which are crucial for regulatory function. So in summary, the hidden Markov models are powerful tools for modeling the sequential data with underlying the hidden states. They consist of states, observation, transition probabilities, emission probabilities, and initial probabilities. Key algorithms for training and using HMMs include the forward backward algorithm for probability computation, the Viterbi algorithm for state sequence decoding, and the Baum-Welch algorithm for parameter estimation. So HMMs find the application in various fields, notably in speech recognition and bioinformatics, where they enhance the ability to interpret and predict the complex sequential patterns. Okay. So now it is time to discuss about the dimension reduction methods. So at the first, dimension reduction is a critical process in pattern recognition aimed at reducing the complexity of data by reducing the number of features or dimensions while preserving the essential information. This is crucial for improving the computational efficiency, mitigating the curse of dimensionality, and enhancing the performance of pattern recognition algorithms. So importance of reducing the dimensions in pattern recognitions, like computational efficiency. So high dimensional data often requires significant computational resources to process and analyze. So dimension reduction reduces the computational burden by working with a smaller subset of features. Okay. So overfitting mitigation. High dimensional data are prone to overfitting, where models learn noise or irrelevant patterns in data, leading to a poor generalization to unseen data. So dimensional reduction helps in mitigating the overfitting by focusing on the most informative features. Visualization. Reduced dimensional represents enable easier visualization of data, allowing for better understanding and interpretation of patterns. Improved performance. So by focusing on the most relevant features, dimensional reduction techniques can lead to improve the performance of pattern recognition algorithms, such as higher accuracy and faster training times. So techniques for dimensional reduction like PCA, principal component analysis, is a widely used linear dimensional reduction technique that identifies the orthogonal directions in the principal components that captures the maximum variance in the data. These principal components are ordered by their variance, and a subset of them can be selected to represent the data in a lower dimensional space while preserving the most significant information. So linear discriminant analysis, LDA, is a supervised dimensional reduction technique that aims to find a linear combination of features that maximize the separation between the classes in the data. Unlike PCA, which focuses on the maximizing the variance, LDA considers the class information to find the discriminative features that are useful for classification tasks. So comparison, PCA and LDA. PCA unsupervised techniques and LDA supervised techniques. Okay. So the performance of dimensional reduction techniques depend on the specific characteristic of the data and the task at hand. In general, LDA may perform better than PCA when class separability is significant, but PCA is often more computationally efficient and suitable for unsupervised tasks. So interpretability. PCA provides the principal components that are linear combination of the original feature, making them less interpretable in terms of class separability. So LDA explicitly considered class information, leading to more interpretable features that are optimized for classification. So dimensional reduction methods like PCA and LDA play a crucial role in pattern recognition by reducing the dimensionality of the data while preserving the important information. While PCA is unsupervised that focus on the computing or capturing the variance, LDA is supervised and emphasizes the class separability. The choice between these techniques depend on the factors such as the nature of the data, the task requirements, and the computational consideration. Okay, so now the part 6. Okay, so non-parametric techniques for density estimation. So what is density estimation? Density estimation is a process of estimating the probability of density function like PDF of a random variable from a set of observed data points. So you already know that in statistics, in engineering mathematics. Okay, so it plays a crucial role in the various statistical and machine learning tasks, including the pattern recognition, anomaly detection, and data visualization. So accurate density estimation allows for better understanding and modeling of data distribution, enabling the more informed decision making. So non-parametric method. Non-parametric density estimation methods do not make explicit assumptions about the functional form of the underlying distribution. Instead, they directly estimate the PDF from the data without assuming a specific parametric model. So two popular non-parametric techniques for density estimation are the kernel density estimation KDE and k nearest neighbors KNN. So kernel density function KDE is widely used for non-parametric method for estimating the probability density function of a random variable. It works by placing a kernel function centered at each data point and summing up the contribution of all kernels to estimate the PDF. So the choice of kernel function like Gaussian and bandwidth parameters significantly influence the smoothness and accuracy of the estimated density. So k nearest neighbors for density estimation. KNN is another non-parametric method that estimates the PDF by considering the local neighborhood of each data point. For a given query point, KNN calculates the density estimate by counting the number of data points within a specified radius or k nearest neighbors and normalizing by the volume of the neighborhood. So the choice of the number of neighbors k and the distance metrics affect the smoothness and accuracy of the estimated density. So comparison like KDE, the computational complexity of KDE depends on the number of data points and the choice of kernels function and the bandwidth, and KNN, the computational complexity depends on the number of data points and the number of neighbors. It is generally less computationally intensive than KDE. Okay, so smoothing. KDE typically produces the smoother density estimates compared to KNN. Okay, so in conclusion, non-parametric density estimation methods like KDE and KNN offers the flexible data-driven approaches to estimate the underlying probability density function. While KDE produces smoother density estimates and is more flexible, KNN provides a simpler alternative with fewer assumptions. The choice between these techniques depends on the factors such as characteristics of the data, computational consideration, and desired level of smoothing. So now it is time to discuss about the linear discriminant function based classifier. So basic concepts like linear discriminant LDA. Okay, so linear discriminant analysis is a supervised classification technique used to find the linear combination of features that best separate different classes in the data. It aims to maximize the combination of features, okay, so between the class variance while minimizing the within class variance, resulting in discriminating functions that effectively separate the classes. Okay, so you can see in this screen the designing of a linear discriminant classifier like Fisher's linear discriminant. Okay, so the formulas. So criteria for designing a linear classifiers like maximizing the class separability, linear decision boundaries, optimizations, robustness. Okay, so linear discriminant analysis and Fisher's linear discriminant provide the effective tools for designing the linear classifier based on the linear discriminant function. So by maximizing the class separability and defining the linear decision boundaries, these techniques enable the efficient and interpretable classification of data with multiple classes. Criteria for designing the linear classifier include the maximizing class separability, ensuring the linear decision boundaries, optimization, and robustness to variations in the data. Okay, so non-metric methods for pattern classification, like non-metric methods in pattern recognition refer to techniques that do not rely on the explicit distance or similarity measures between data points. Instead, they focus on learning decision boundaries or patterns directly from the data without the needs of predefined metrics. These methods offer the flexibility and can handle the complex data distribution and relationships. So non-metric approach in pattern recognition encompasses a wide range of techniques including the decision tree, random forest, neural networks. Okay, so these methods leverage the different algorithms and principles to learn patterns from the data and make predictions or classifications. So key technique like decision tree. At first, it is a hierarchical tree, a structure that recursively partitions the feature space based on the values of input features. Each internal node represents a decision based on the specific feature, and each leaf node represents a class level for prediction. Decision trees are intuitive and easy to interpret, making them suitable for both classification and regression tasks. However, they may suffer from overfitting, especially with complex datasets. So, random forest. Random forests are ensemble learning method that combines the multiple decision trees to improve the predictive performance and reduce the overfitting. Each tree in the forest is trained on a random subset of the training data and the random subset of features. During prediction, the output of individual trees are averaged or aggregated to produce the final prediction. So random forests are robust and can handle high dimensional data, noisy data, and missing values effectively. So neural networks. Neural networks are the class of machine learning models inspired by the structure and the function of biological neural networks. They consist of interconnected layers of artificial neurons, each performing a simple computation. Neural network can learn complex nonlinear relationships in data and are capable of solving a wide range of pattern recognition tasks, including the image recognition, speech recognition, and natural language processing. So deep neural networks in particular with multiple hidden layers have shown remarkable performance in various domains. Okay, so in conclusion, non-metric methods for pattern classification offer the diverse approaches for learning patterns from the data. Okay, so now unsupervised learning and clustering. So unsupervised learning is a branch of machine learning where the algorithm learns the patterns and the structures from unlabeled data without explicit supervision or guidance from the target variable. Unlike supervised learning where the algorithm is trained on labeled data to make prediction or classification, unsupervised learning aims to uncover the hidden structure or relationships in the data. So difference between the supervised, like in supervised learning the algorithm is provided with label training. Okay, so clustering techniques. Clustering is a fundamental and unsupervised learning technique that partitions the data set into groups or clusters of similar data points. Clustering algorithms aim to maximize the intra-cluster similarity while minimizing the inter-cluster similarity. Okay, so it maximizes the intra-cluster similarity and minimize the inter. So some common clustering techniques including the k-means clustering, hierarchical clustering, and density-based clustering, DBSCAN. Okay, so k-means clustering. K-mean is a popular partition clustering algorithm that divides the dataset into k clusters by iteratively assigning the data points to the nearest cluster centroid and updating the centroid based on the mean of the data points in each cluster. So k-mean is efficient and scalable but requires the number of clusters to be specified a priori and may converge to local optima. So hierarchical clustering. Hierarchical clustering builds a hierarchy of clusters by recursively merging or splitting the cluster based on distance or similarity measures between the data points. It does not require a number of clusters to be specified beforehand and can produce the dendrograms. So remember dendrogram in hierarchical clustering to visualize the clustering structure. So however, hierarchical clustering like agglomerate, divisive, okay, can be computationally expensive, especially for large data sets. So density-based clustering. So DBSCAN is a density-based clustering algorithm that groups together the data points that are closely packed in a high-density regions and separates the regions of low density. It does not require specifying the number of clusters and is robust to noise and outliers. So DBSCAN identifies the core points, border points, and noise point based on the distance and density thresholds. However, it may struggle with datasets of varying density or irregular shapes. Okay, so unsupervised learning encompasses the technique for learning patterns and structure from the unlabeled data. Okay, so at the end of the video, as we reach the conclusion of our exploration into pattern recognition, we have uncovered its fundamental principles, advanced algorithm techniques, and practical applications. Remember, the pattern recognition is not just about algorithms, it is about understanding the world around us. So whether you are a novice or a seasoned practitioner, may this video inspire you to delve deeper into this captivating field. So as you continue your journey, embrace the curiosity and innovation and the pursuit of knowledge. So thank you for joining us on this enlightening adventure. Farewell, and may your future endeavors be filled with pattern recognition. Okay, so thanks for watching, and like, share, subscribe our channel for more videos. Okay.